Okay, in this video, we are developing general relations for internal energy, enthalpy, entropy, and specific heats. This is part of chapter 12 of the textbook that we are using. So let's start with the internal energy. So I do the internal energy first, and then we do the enthalpy and other properties. For internal energy or U, let's assume that U is a function of temperature and a specific volume. So basically, we choose internal energy U as a function of temperature and specific volume. Okay, so basically, if U is depending on two properties, I can utilize the general form of total energy. The general form of total derivative. So dz in general is partial z partial x when y is constant multiplied by dx plus partial z partial y when x is constant multiplied by dy. So this is the general form, right? This is the general form when z is a function of x and y. Now here, in this case, my z is internal energy U and x and y are temperature and specific volume. So that means I can apply the same total derivative to function u. So basically du is equal to partial u partial t when the specific volume is constant multiplied by dt plus partial u partial v when temperature is constant dv. Okay, so all I did, I applied this concept into this correlation. Okay, so this is in fact my specific heat at constant volume. This is my CV, specific heat at constant volume. The change of internal energy with respect to temperature while the volume is kept constant. So basically I can say du is equal to CV dt plus partial u partial v when the temperature is constant dv. My goal is to come up with a correlation for internal energy U. Right now, I'm very close to my goal because this part is good, the second term is good. If I can somehow manipulate the second term on the right hand side, then I have achieved my goals. Let me call this equation 1 star. And what I'm going to do for the next step, I am going to choose function S based on temperature and specific volume. Okay, so if I do that, once again I can do this concept or this total derivative for s, and that will be ds is equal to partial s partial t when volume is constant dt plus partial s partial v when temperature is constant dt. Okay, now what I'm going to do, I'm going to recall one of the equations we had before, and that equation was du is equal to tds minus pdv. Okay, so previously we had this equation, and this is simply coming from applying the conservation of energy. So let me show you when we had this correlation. If you remember, whenever we're discussing about Maxwell relations, I utilize the conservation of energy on a differential system, and then for an internal reversible condition, dq was equal to tds. Likewise, dw was equal to pdv, so we could come up with this correlation. So we had this before. I'm using that once again here. Okay, now what I'm going to do, I'm going to combine this equation du with this equation. So basically the the ds that I have in this equation, this ds is going to be replaced with the right hand side of this equation. So basically my du is going to be t. Instead of ds, I will have this one here, which is partial s partial t when volume is constant dt plus all right, there's a typo here. So this should be partial s partial v when temperature is constant multiplied by dv. So correct this. Sorry about that. This should be dv. Okay. So partial s partial t when volume is constant multiplied by dt plus partial s partial v when temperature is constant dv. Okay. So again, I'm rewriting this equation by replacing ds with the right hand side. So I'm done with the first term, and then I have minus pdv. Minus pdv. Okay, now I have two dv terms. Let's put them side by side. So again, rewriting this equation, du is basically t partial s partial t when volume is constant dt plus, then putting these two next to each other, t, which is this one, multiplied by this, partial s partial v when temperature is constant, minus p, the whole thing is multiplied by dv. Okay, now let me call this equation equation 2 star. So initially I had 1 star, now that is my 2 star. So 1 star and 2 star are, in fact, both of them are du. If you look at them, they are both du. So what I'm going to do, I'm going to equal them and then manipulate the right hand side of each equation. So by equaling this equation with this equation, the coefficient of dt should be the same, like this should be equal to cv. So cv is going to be equal to t partial s partial t when v is constant, which based on that I can make a conclusion that cv over t is going to be equal to partial s partial t when volume is constant. All right, and let me just make it clear that what I'm doing, I'm equaling 1 star with 2 star here. So this is one of the conclusion. So once again, the first line comes from the fact that if these two correlations are equal, then both of them are du on the left hand side. That means the right hand side should also be the same. So that means the coefficient of dt that I have here should be equal to each other. So cv is equal to this. That is exactly what I have here. Likewise, the coefficient of dv should be the same, like this bracket should be equal to partial u partial v when temperature is constant. So partial u partial v when temperature is constant here is equal to this bracket, t partial s partial v when temperature is constant minus p. Okay, I will be using these two later on for entropy correlations. So will be used later. We come back to these later for entropy correlations. Now, what I'm going to do, I'm going to apply one of the Maxwell relations we have on this correlation. If you remember, one Maxwell relation said partial S partial V when temperature is constant is equal to partial P partial T when volume is constant. Okay, so we had 4 Maxwell relations and this was one of them. Now let's rewrite this by using this concept. Then I could say partial U partial V when temperature is constant is equal to T. Instead of partial S partial V for constant temperature, I write this one here. I would say partial P partial T when volume is constant minus P. Okay, so this is basically rewriting this based on the Maxwell correlation. Let me call this correlation 3 star. Okay, if I get back into this correlation, I need to be careful. Here I made a mistake, in fact, because in this line I was equaling this coefficient of dv, so this is dv, I was equaling this one with this one. So here that's partial S partial V for constant temperature. Here on the right hand side here, T only is multiplied by partial S partial V. So in fact this bracket should not be up to here. This bracket only should be up to here. And this is wrong. Let's see if I can find my... Okay, so let me... Where was I here? This needs to be corrected. So sorry about that. Correct your notes. So make sure that you have this right. And because of that, again, I need to have T only multiplied by this. Okay, now this is the correct form. Like right now, only temperature. Temperature is only multiplied by the first term, not to the pressure. So pressure is outside of the bracket. Okay, for the next page, I am going to continue by equaling 1 star to 3 star. So for next page, I would say, so you can see, I would say trying to have 1 star in the field of view, it's pretty tough. Okay, so 1 star and 3 star give me this conclusion. They will give me du is equal to cv dt. So basically I'm doing here plus, instead of partial u, partial v for constant temperature, I'm utilizing this correlation. Plus t partial p partial t for constant volume minus p, the whole thing is multiplied by dv. So basically this equation is the same as equation 1 star here, but what I changed was this term. So I changed this one with 3 star, replaced with 3 star. That's all I did. So I don't need this page anymore. Okay, so finally we have achieved our goals, because by integrating, this is what we will get. We will get u2 minus u1 is equal to t1 to t2 cv dt, okay, plus v1 to v2 specific volume 1 to specific volume 2, this bracket, t partial p partial t for constant volume minus p, the whole thing as a bracket multiplied by dv. Okay, so this is the general equation we were looking for. So this equation gives us the change in internal energy, and we can utilize that to calculate the change of internal energy when the temperature is changing and when the specific volume is changing. For the next step, we are doing the same concept, but this time for enthalpy. So initially I did for internal energy. Now let's do pretty much the same thing for enthalpy. I'm going to choose H to be a function of temperature and pressure. So H is chosen to be a function of temperature and pressure. So based on that, I can say dH is partial H partial T when the pressure is constant multiplied by dt plus partial H partial P when the temperature is constant multiplied by dP. Okay? So once again, for this correlation, I am applying this concept that we had earlier. So earlier, at the very beginning, we said that if z is a function of x and y, then dz can be written like that. So right now I'm doing the same thing, but considering z being enthalpy, and x and y being temperature and pressure. So that gives me dH. So based on the definition, this is in fact our specific heat at constant pressure. This is my Cp, right? So if I can manipulate the coefficient of dP here, then I have achieved my goal. My goal is to obtain an equation similar to this, but for enthalpy H. So our product will be looking something like this, but instead of U, we will have H on the left-hand side. So now let's assume or choose S to be a function of temperature and pressure. Okay, so if I do that, then I can say ds is again the same concept, is partial S partial T for constant pressure multiplied by dt plus partial S partial P for constant temperature dP. Okay, also previously I showed that dH is equal to TdS plus VdP. We had this before. If you're asking where this comes from, this is coming from here. If you remember, I was saying I was applying conservation of energy on a differential system. Then this was the first equation that we had before, and then by writing H as a by writing H based on U plus PV, then dH can be developed like that. If you simplify that, you will end up with dH is equal to TdS plus PdV. So this is exactly what I have here. Okay, so let me call this equation, by the way, 1 star. And let me utilize this correlation and rewrite dH. So what I'm going to do, I'm going to rewrite this dH, but instead of ds, I will write the right hand side of this correlation. So basically that gives me dH is equal to T. Instead of ds, I have the right hand side here, and that is partial S partial T when pressure is constant dt plus partial S partial P when temperature is constant dP. So the entire bracket is my ds in fact. Okay, and then I will have plus VdP plus VdP. So basically the whole thing here is my ds. Okay, now I can rewrite this equation dH by putting these two terms next to each other. So that will be T partial S partial T for constant pressure dt plus T multiplied by partial S partial P for constant pressure plus V, the whole thing multiplied by dP. Okay? Now let me call this correlation equation 2 star. So if you notice, 1 star and 2 star are both dH. Like here I have dH, here I have dH. So that means the coefficient of dTs should be equal and the coefficients of dPs should also be equal, exactly like what we did before. Okay, so by equaling 1 star and 2 star, I'll get two conclusions. The first conclusion is the coefficient of dt here is equal to the coefficient of dt here, which is Cp equal to T partial S partial T for constant pressure. Okay, that is one of the conclusions of equaling these two. The second conclusion is the coefficients of dPs are equal to each other. That is partial H partial P for constant temperature is equal to T partial S partial P for constant temperature plus V. Okay? Now, I am going to use one of the Maxwell correlations that we had. One of the Maxwell correlations said partial S partial P for constant temperature is equal to negative partial V partial T for constant pressure. Okay, let me find that correlation so I can show you here. SPVP. All right. So basically, I am referring to this Maxwell correlation that we had before, the second one. I'm using the second Maxwell relation. Okay, so this is Maxwell relation. So if I use that, then one thing I can do, I can rewrite this correlation, but instead of partial S partial P for constant temperature, I can write this thing here. Okay. So basically, this way, 1 and if I call this one 3, so let me, okay, before doing that, let me do one thing. Let me just rewrite this equation, that is partial H partial P for constant temperature is equal to T. Instead of partial S partial P for constant temperature, I will use this one. And there is a negative sign, so I put negative T partial V partial T for constant pressure plus V. So basically, this equation is coming from here. So I rewrote this equation, but instead of, I rewrote this equation. I rewrote that equation. Partial H partial P for constant temperature is T, and this one has a negative sign. So basically, all I'm doing, I'm replacing this with this, because this is the left hand side here. Okay, now let me call this one equation 3 star. For the last step, I'm going to combine 1 star with 3 star. Okay, because one thing I have in equation 1 star is partial H partial P for constant temperature, which is the left hand side here. So I'm going to replace this one in 1 star with the right hand side of 3 star. So replace with the right hand side of 3 star. Okay, so that tells me dH is equal to Cp dt plus V minus T partial V partial T for constant pressure multiplied by dP. Okay, so dH is Cp dt plus V minus T partial V partial T for constant pressure multiplied by dP. Now I have achieved my goal because I can obtain H2 minus H1 by simply integrating this equation. So that gives me H2 minus H1 being equal to T1 to T2. This is T1. T1 to T2 Cp dt plus P1 to P2, the entire bracket. V minus T partial V partial T for constant pressure dP. Okay, and also I know that H2 minus H1 is equal to U2 minus U1 plus P2 V2 minus P1 V1. So these V's, by the way, they are specific volumes. Okay, so this is the equation I was looking for. After all this math, we obtained this equation, which technically gives us the change in enthalpy by getting this integral from T1 to T2 and also this integral from P1 to P2. For the next step, I will do the same concept but for entropy. So after U and H, we can develop correlations for entropy. So my goal is to obtain an equation for change of entropy similar to what we did for U, internal energy, and H, enthalpy. So in order to do that, I am going back to the page that we had correlations for internal energy, and I'm going to call two of the equations that we used there. So one equation that we had there was this one, okay, and the other equation that I'm going to use is this one. Oops, you cannot see, so let me bring it up. So the other equation that I'm going to use is this one. So basically this is one of the equations I'm going to use. This is the second equation I'm going to use along with one of the Maxwell relations. So I'm going to copy this equation, and after that this equation, and then the Maxwell relation, and just combine all them together. So the equation that I'm borrowing from internal energy is ds equal to partial s partial t when specific volume is constant multiplied by dt plus partial s partial v when temperature is constant dv. So this is coming from before. Also, one of the equations we had from before was cv over t is equal to partial s partial t when volume is constant. And also, I am going to use one of the Maxwell relations that we had before. And the one that I'm going to use, so these are the Maxwell relations we had, there were four. I'm going to use the very first one, which gives us partial S partial V for constant temperature, because this is exactly what we have here. Okay, so let me just copy the Maxwell relation. It says partial S partial V for constant temperature is equal to partial P partial T for constant specific volume. Okay, so I am going to rewrite the ds equation, but instead of partial S partial V for constant temperature, I'm using this Maxwell relation. So this is the Maxwell relation that I have. And in case you are asking where these two equations came from, you already have them. Go to your internal energy notes, we did them there. So from internal energy notes. Also here, from internal energy notes. Okay, so once again, instead of partial S partial V for constant temperature, I'm rewriting this one. So this is basically going into here. And instead of this one, partial S partial T for constant volume, I'm writing this. So instead of this, I will have this thing. Now let me rewrite the ds correlation. So ds is going to be, instead of this, I will have cv over t dt. So this dt is this dt plus, instead of this, I will have partial p partial t constant volume dv. Okay, for the next step, all I'm going to do is just to get the integral, because by getting the integral, I would have s2 minus s1 is equal to t1 to t2 or multiplied with cv over temperature dt plus, now volume 1 to volume 2, and these are specific volumes, by the way, partial p partial t constant volume dv. Right, so this is the equation I was looking for the entropy changes. So far we have done equation for internal energy. So this was the equation we had for internal energy. We did that before. And then after that, we did for enthalpy. So this was the equation for enthalpy. Okay. And then at the very end, we did for entropy.